So today we'll be solving the following problem in which we're given that x1 and x2 are subspaces on R given by x1 is equals to 0, 1, union 3, 4 and x2 is equals to 0, 1, union 1, 2. We have to determine whether x1 and x2 are homeomorphic or not. Now, given that x1 and x2 are topological subspaces of R in the Euclidean topology, we can denote their respective subspace topologies by τ1 and τ2, forming the following topological subspaces. Now, we want to show that there exists a homeomorphism F between these two topological subspaces where τ1 and τ2 are Euclidean subspace topologies. To do this, we have to show that the following conditions of homeomorphism are satisfied. Let's list out the necessary conditions for F to be a homeomorphism between x1 τ1 and x2 τ2. The first is that F must be bijective. The second condition is that F must be continuous. And the third and last condition is that the inverse of F is also continuous. So, if we can define a function F that satisfies these three conditions, we can say that there exists a homeomorphism between x1 τ1 and x2 τ2. So, let's do that. Let's define a function F as the following. So, let's find F as f of x is equals to x when x is in the open interval between 0 and 1, and f of x is equals to x minus 2 when x is in the open interval between 3 and 4. Let's also draw this out so we can visualize it a bit better. Here, let's say that this is our x and this is our f of x. So let's also write this out: 1, 2, 3, 4, and we can do the same over here: 1, 2, 3, so on. What would this function look like? So we know it's an open set, so it is not going to contain the point 0 and the point 1. However, we know that f of x is equals to x in between that, so this will be a straight linear function. And then when when x is in the open interval between 3 and 4, we know that f of x equals to x minus 2. So that maps onto 3 minus 2, which is 1. And again, since it's an open interval, it doesn't contain the point 3 or 1. And 4 minus 2, we get 2. So again, it doesn't contain 2 or 4. However, it contains everything in between it. So we know that this is what our function looks like, and this is how it maps between the two. We can already notice that our domain is x1, since x1 is 0, 1, union 3, 4, and we can see how it is mapping on to our codomain, which is x2, as it's mapping on to 0, 1, and union 1, 2. So this is the function we've defined. Now let's go step by step to show if f is a homeomorphism between x1 τ1 and x2 τ2. To do that, let's first start by the first condition. Let's show that f is bijective. So now we know that in order for f to be bijective, it has to be both injective and surjective. So let's start by first looking at injectivity. So in order for f to be injective, we know that f must map every unique element from the domain onto a unique element in the codomain. So let's look at our domain and codomains. We know our domain is 0, 1, union 3, 4. And our codomain is 0, 1, union 1, 2. Right. So let's look at the first interval, 0, 1. Now, given that f of x is equals to x is a linear function mapping 0, 1 onto 0, 1 as f of x is equals to x, we know that for all elements between 0 and 1, it maps them onto unique elements in 0 and 1. For example, 0.5 will map onto 0.5, 0.6 will map onto 0.6, and so on and so forth for all elements in 0 to 1. And it's the same case for x in 3 to 4. We know that since it's a linear function, it's a straight line, it is mapping everything in x onto a unique thing in y, or in f of x. So let's write that down. F maps every x1 in 0, 1 to a y1 in 0, 1, given that f of x is equals to x. It also maps every x2 in 3, 4 to a y in 1, 2, since we know that f takes everything from our domain 3, 4 and subtracts 2, which takes us to our codomain, so from 3 to 4 to 1 to 2. Now since they're both open sets, we can say that for all x in x1, since x1 is 0, 1, union 3, 4, for all x in x1, f maps x to a unique y in x2, since x2 is the union of y1, 0, 1, and 1, 2. So x2 is equals to 0, 1, union 1, 2. So we have shown that f is injective. Now, in order for it to be bijective, it also has to be surjective. So let's look at surjectivity. Now, in order for f to be surjective, for all elements in the codomain, there exists an element in the domain that such that f of the element in the domain is equals to the element in the codomain. So, like for all elements over here, there has to be an element from the domain that maps onto. So there can't be anything in x2 that isn't being mapped to that isn't being mapped onto by an element from x1. Now, again, let's take the same approach and let's look at our codomain 0, 1, union 1, 2. Let's look at the first part, 0, 1. Now, for all y in 0, 1, we know that the function f of x ensures that since f of x is equals to x, so for all x2, for all elements in 0 to 1, there is an element in 0 to 1 that is mapping 0 to 1 onto 0 to 1, right? So when we write that down, we can write for all y1 in 0 to 1, our function f of x is equals to x for x1 in 0 to 1 results in, okay, so for all y1 in 0 to 1, f of x is equals to x ensures, actually wait, f of x is equals to x for x1 in 0 to 1 ensures that f of x1 is equals to y1, and the same is true for all y2 in 1, 2. F of x is equals to x minus 2 for when x2 is in 3, 4 ensures that f of x2 is equals to y2. Now, since x1 is the union of 0, 1 and 3, 4, and x2 is the union of 0, 1 and 1, 2, we can say that f ensures that there exists an x in x1 such that f of x is equals to y.
For all y in x2.
In which y is in x2. And since this statement shows that f is surjective, we have shown that f is injective earlier, and what that results in is us having shown that f is indeed bijective. So f is bijective. Now we have to show the remaining two conditions, which are that f is continuous and the inverse of f is continuous. Now, to show that f is continuous, we will be using the following proposition from class. So let f be a function between x1 and tau 1 to x2 and tau 2 with basis beta 2 for tau 2. Then f is continuous if and only if the preimage of b is open in tau 1 for all b in beta 2. So we will use this proposition to show that f is continuous. Now, since x1, tau 1, and x2, tau 2 are Euclidean subspace topologies, beta 1 and beta 2 consist of all the sets that are intersections of x1 with all open intervals of the form ab with a less than b in R, and the intersection of x2 with ab with a less than b in R, respectively. So let's write that down. So since they're in the Euclidean subspace, this is what beta 1 would look like. Beta 1 would be an intersection of x1 with any open interval in which a is less than b in the real numbers. And beta 2 would be x2 intersection with ab in which a is less than b in R. So these will be the basis for x1 and x2. Now let's see what this is going to look like. So let's just for our own visual aid write this down. So we have this as x1, oops, and we know that it is being mapped onto, actually this might be too big. There we go. And we know that f is mapping this on to 0, 1, union 1, 2. So we have two disconnected open intervals mapping onto two disconnected open intervals. Now, let's see what the basis elements of this would look like. So let's look at beta 2 first. So if we were to intersect x2 with any interval, any open interval in R, here are the possible cases. What might be? It could be that a is less than 0, so it's starting before 0, and and b is, let's say b is 1, so it is outside this interval but also before this interval. So what that would give us as basis element is going to be the entire open set 0, 1. And when we look at the preimage of this element b in beta 2, we know that the preimage of 0, 1 is going to be 0, 1, which is open in tau 1. And the same is the case for any interval between 0 to 1. If a and b were between 0 and 1, for any open interval, it will map it onto an open interval between 0 to 1 over here, and that will also be open. And the same is the case between this segment and this open interval. If a is equals to 1 and b is greater than 2, then the intersection between the two would be the open set 1, 2, which would have the preimage of 3, 4, which will be open in tau 1. And for anything, any open interval in between 1 and 2, the preimage for that would be in between 3 and 4, which would also be open in tau 1. However, let's consider the case in which a is greater than 0, is less than 1, and b is greater than 1 and less than 2. So when we intersect with an open interval like this, what we're getting is we have our first point somewhere in here, and we have our second point somewhere in here. So the intersection between the two of those would give us an open set that would look like this. It would look like A1 union 1 B. However, it's important to note that this is an open interval, and this is an open interval, and the union of two open intervals is open. We get an open interval when we intersect the open interval with x2, and the preimage of this is going to map onto a1 for this, and then for 1b, the preimage is going to be from 3 up until the preimage of b
Plus 2.
set, which will also be an open set, as it is the union of two open sets. And the same is true for any intersection that we can take in x2, whether it's partially contained within this or fully contained within this, or it is half contained in this and half contained in this between the two open intervals, or however we might take it. The preimage of that is going to be an open set in tau 1, as the function that we've defined gives us a preimage that is a union of two open sets, which is open. So given that reasoning, we can say that f is continuous, as for all basis elements for beta 2, which is the basis for tau 2, the preimage of it is open in tau 1. And therefore, by this proposition, f is continuous. Now, the only condition that's left to satisfy is the inverse of f is continuous. And to do this, we use the same proposition as we used to prove that f is continuous. However, we tweak it slightly to prove our point. But it's the same idea and the same logic, in which if we let f be a function from x1 tau 1 to x2 tau 2, with basis beta 1 for tau 1, then the inverse of f is continuous if and only if f of b is open in tau 2 for all b in beta 1. So we have just changed the basis, and instead of proving if f is continuous, we're proving if the inverse is continuous. So using the same logic, we can find the same proof in which we know that beta 1 consists of the intersection of x1 with any open interval in R. It's the collection of all those sets a, b, and R with x1. Then we have so that is x1, and this is x2. So yeah, f is mapping x1 onto x2. Then when we consider our basis for tau 1, when we consider beta 1, and we look at what elements of beta 1 would look like, it would be the intersection of this with any open interval in R. So using the same logic, if we have a less than 0, so this a is over here, and b is between 1 and 3, we're going to get all of the open set 0, 1, and f of 0, 1 is going to be 0, 1, which is open in tau 2. And anything in between this is going to map onto anything in between this, and therefore it will also be open in tau 2. The same is the case if we get a to be between 1 and 3 and b to be greater than 4. We'll get the entire set 3, 4, which will be an element of the basis, and f of b will map onto 1, 2, which will be open in tau 2. And similarly as the previous case, if we were to take any such interval in which a is in between 0 to 1 or before 0 and 1, and b is in between 3 and 4 or after 3 and 4, the basis element that we would get in such a case would be if a is in between 0 and 1, if a is greater than 0 and less than 1, then this will be, and b is greater than 3 and less than 4, then this will be our basis element. And when we plug this into our function, we see that a to 1 will map a to 1 will map onto a to 1 as f of x is equals to x, and 3 to b will map onto 1 to b minus 2, which since we know that b is less than 4 will be in between 1 and 2, which will also be an open interval. Yeah, we know that this will map onto a1 union 1 and then 3 minus or b minus 2, in which b is greater than 3 and less than 4, so it's going to be a value between 1 and 2, which will be an open set, which is open in tau 2. So we can say that we can generalize this, and we can say that no matter what open interval we take from R, whatever basis, whatever element of the basis that we get, whatever b in beta 1 that we get, we know that that f maps that open set on to an open set in tau 2, and because of that, given our proposition, we know that the inverse of f is also continuous. So what that does is it shows that all of the given conditions of a homeomorphism are being satisfied, and therefore f is a homeomorphism. And that f is a homeomorphism as it is, we show that it is bijective, it's continuous, and the inverse of f is continuous, and all the conditions are satisfied, and therefore the x1 tau 1 and x2 tau 2 are homeomorphic to one another. It's also interesting to note that just how connectedness is preserved under homeomorphism, we also get to see how disconnectedness is preserved under homeomorphism. Although this is not proof that shows that rigorously, we just see an example of how disconnectedness is being preserved under homeomorphism. And yeah, that concludes our proof, and we have shown that x1 and x2 are homeomorphic to one another.